Welcome back to our first lecture, this third part of our lecture. And in this part, I'm going to go from regression to machine learning methods. Okay? So I'm going to start with the intuition behind linear regression. Then I'm going to show you linear regression as a machine learning model. Then I'm going to discuss a little bit about the challenges in high dimensions. And I'm going to end this lecture by introducing you to some of the penalized regression models. So let's start with an example. Let's suppose that we want to predict wages, okay? So I'm taking data from this paper by Blackburn and Newmark on observability, efficiency, wages, and inter-industry wage differentials published in the Quarterly Journal of Economics in 1992, okay? So imagine that you have wages from 758 individuals in 1980. Okay? And assuming that only wages are observed, one interesting question is, what's the best predictor for the yearly wage of a new individual? Okay? So imagine this is the histogram. What you're seeing here is the empirical distribution of the wages in our sample. And we want to know, okay, give me a new individual. What is my best guess for his wage? Okay. The mean, why is the mean? So the mean is the best predictor because the expected value, the population mean, is the best predictor in the mean squared error sense. So if we take optimization problem, remember our previous block where I defined for you the risk function. So take this function here, that will be the expected value of the square differential. So that's the loss function, and the expected value of the loss function is our risk function. And we want to find a parameter theta that minimizes that risk function, that minimize the mean squared error. So in this case, we can show that mu, the expected value of y, therefore the mean, is the solution for that minimization problem. Okay? Here is the proof. It's a very simple proof. Basically, you have to open this square here, and you're going to see that very easily we can show that the expected value of y is the best predictor. Okay? So in practice, we need to estimate the mean. How we do it? Instead of looking at the risk, we look at the empirical risk for a sample of t observations. So we have t observations, and we want to minimize the empirical counterpart of the theoretical risk that I defined in the previous slide. Okay? So we want to minimize the sum of the squared errors. Okay? So if we take the derivative of that function and making it equal to 0, that's what we have. And then we can solve that this way. And in the end, what we get is that the mu hat, our estimator, will be given in terms of the average. So an estimate of the mean is just the sample average. Okay? Suppose now that we observe if an individual lives in a metropolitan area or not. Call it this variable MRT. Okay? So what we can see here is the distribution of individuals that lives in a metropolitan area, the blue curve, or individuals that don't live in the metropolitan area, the red curve. See that the one curve is a little bit shifted to the left, or here shifted upwards. Okay? So the mean is slightly different from people that live in a metropolitan area and then people that live in a rural area. Okay? So we want to know what's the best predictor, theta, of wages, given that we observe the variable MRT. Okay? So the condition expectation is the best predictor also in the mean squared error sense. In an analogous way as the case that I showed in the previous slide. Okay? So the condition expectation is optimal in the conditional mean squared error sense. So what we have here is that we take, this is our loss function, so it's the square loss. We are going to take the expected value, and because we observe, we want to condition on this MRT term, we have to condition, this expectation should be conditional on MRT. Okay? So, what we are going to do here is a trick of adding and subtracting a term. So we are going to add the condition expectation of y given MRT, and we are going to subtract the expectation, the condition expectation of y given MRT. Okay? So therefore, we can combine terms. We are going to take one y and one condition expectation. Remember, there's a square here. We have the square of this term, the green term, then the square of the blue term, that will be the square of the difference of the condition expectation and the function theta, plus 2 times the cross product of these two terms. Everything conditional on MRT. Therefore, what we have, we can separate this into 3 terms. We have one term here, the green term, the blue term, and then the magenta term. Okay? So basically what we see is that this term here will be 0 if theta equals to the condition expectation. The same here. Okay? And one tricky part is that you're going to see that if by any chance you do not add or subtract the condition expectation, if for instance if you add or subtract any other function, okay, these 2 terms will be cancelled, making theta equals to that function, but that term here will be greater than this one. So basically, plugging the condition expectation here will make this first term achieve a minimum value. Okay? So what we have is that this function theta will be equal to the condition expectation. Okay? This is one way of proving the result without any calculus. Of course, a much more elegant way is to take derivatives of that function, make them equal to 0, and solving for theta. And you're going to see exactly the same result, that theta, the optimal theta, is the condition expectation. Okay? So the condition expectation is optimal in the conditional mean squared error sense. How we estimate that? In a very similar way. We take the average, the sample average of the individuals that live in a metropolitan area, and we take the average of the individuals that do not live in the metropolitan area. So it's a very simple estimator. We just take 2 averages based on the observation of this binary variable MRT, because MRT can take only values 0 or 1 or yes or no. So it's a binary variable. So it's very easy to compute the condition expectation. Okay? There's no model assumption, we don't need to assume any model for the condition expectation. There's a natural estimator for it, okay? Because we are just segmenting with respect to a binary variable. Okay? But suppose now that we observe schooling, another variable in the database, schooling in years, we call this variable school, okay? And you see here that we have individuals with 9 years of schooling up to 18 years of schooling, okay? So, and you see the samples, different colors indicate the number of individuals in each class. As before, the condition expectation is the optimal predictor in the MSE sense. If we want to predict wages based on schooling, okay? So how can we do that? Still pretty easy. We can compute averages for each year of schooling. Although in some cases we don't have many observations, of people with just 9 years of schooling, but it's feasible. We can compute this estimator. However, we have a problem. How we should predict the wage of an individual with more than 18 years of schooling? Someone who has masters, PhDs, 2 PhDs. How can you do that? Or how can you estimate the wage of someone who has no schooling? This can happen in very poor countries. Okay? How can you do that? You don't have any observations, so you cannot compute the averages. So what we need is a model for the condition expectation. But which model? So pause the video right now, think a bit. Which kind of model you are going to choose? Or you may say, no, I'm working with a population where I'm not going to have anyone with more than 18 years or less than 9. Okay, that's a valid assumption. But if this assumption is not true, how can you determine which is the model for the condition expectation? Okay, so the problem is now a little bit trickier than what we had before when we were conditioning on a binary variable. Now the problem is more difficult. Okay? Let's make it even more difficult. Now we are going to condition on experience in years, work experience. Now it's a continuous variable. So we do not have classes, it's a continuous between 0 up to 20 plus. So we have a distribution here of experience, the distribution of wages. So we need, again, the condition expectation. But now we need a model, right? Because we cannot segment data, we cannot make assumptions about range of experience. So we need a model. Which model? So if we want to uncover the condition expectation of the wages given experience, we need to make an assumption about which class of models we are looking at. So remember the previous block. When we had a supervised learning problem, we have to figure out what's the link, the mapping between the x's on the right-hand side of the equation and the y's on the left-hand side of the equation. Here the x's is experience and the y's the wage. So I want a relationship to uncover the relationship between experience and the wages. Okay? So we can make it linear, the yellow line that you're seeing on the screen, or we can make quadratic, the purple, or we can make a 5th-degree polynomial, the red line, or something crazier, the 10th degree polynomial. That's the green line. Which one? Which model is the best? That's what this course will answer. Which model should we choose? Okay. So, in general, we can represent any pair of random variables, y and x, with a model like this. Like y is a function of the conditional expectation plus a random term. So this conditional expectation will be our function f of x. And by construction, this error term here has condition expectation equal to 0. Right? How can you see that? Well, take the condition expectation of y given x. This is the condition expectation of the condition expectation given the condition given x plus the condition expectation of u given x. So this will be the condition expectation of y given x. This here is exactly expectation of y given x plus expectation of u given x. So these two cancel out. So we have condition expectation of u on x equal to 0, what we intend to show. Okay, so this is a well-known result. The only thing we need is that condition expectation here to exist, right? So what's u? U is the prediction error that represents the variation of y that's not explained by x. Okay? What's the simplest form of f for f of x that we can imagine? Linear. So let's start with a linear model. So y is a linear function of x. This is the simple linear regression model. So we call y the dependent variable, x is the predictor or the covariate or the regressor or the independent variable. Many names to represent this variable x. Okay? In most relevant applications, of course, we are not interested in one single predictor, but we have like multiple predictors. So we want to explain wages by experience, if the individual lives or not in a metropolitan area, by schooling and other variables. So in fact, we want to relate y to a set of predictors, to p predictors. This is the multiple linear regression model. Okay? We are assuming that the relationship between y and the axis is linear. That's an assumption. In some cases, it's a good assumption. It gives us very good results, the linear regression model. In other cases, this is not a good assumption. Okay? We are going to learn techniques to let the data tell us if this is a good assumption or not. Okay? So under very mild conditions, the parameters beta can be estimated by minimization of the sum of squared errors. Okay? In our example, we have MRT, school, and expert as our regressors. Y is the dependent variable, is the wage. Okay? In the original paper, they consider many other regressors. Okay? The question is the linear model always a good option? Advantages: simple, easy to estimate, easy to provide interpretation. Okay? Sometimes linearity is not a good option. We have alternatives. Okay? So for example, a linear model for wages can generate negative predictions because there's no restrictions that predictions must be positive. In this case, there is an easy fix. Write a model for log wages. So you write that, you can just say that log of y is equal to beta naught plus beta 1 x plus u, for instance. Okay? In this case, the predictions for log y are not restricted, but this will induce positive predictions for wages. Okay? So this is kind of an easy fix. We introduce mild nonlinearity. Okay? We can also write models for a much more flexible way, that we are basically saying that the nonlinear transformation of y is a function, it's a linear function of nonlinear transformations of the axis. We call this model nonlinear in the variables, but they are linear. These kind of models, they are linear models in the parameters, because you can write it as a linear function of these transformed variables. Or you can go much more flexible and just say that you have a transformation of y which is a general nonlinear function of the axis. Okay? So this is a much more general model. Problem is something that we are going to deal along the course, is overfitting. Maybe you start, if you do not estimate this function very carefully, what you end up fitting is the random term and not the dependence on the axis. So what we want to learn is the function of f. You don't want to learn the noise. This is noise, this is error. You want to learn f. So depending, if you really go crazy and try to estimate a highly nonlinear model or highly nonlinear transformed variables, you have the risk of ending with an overfitted estimation. Okay? And another problem here is what happens when you have more variables than observations. P, the number of variables, is larger than the number of observations. And now we can make a pause, because I think we reached the main point of this course. Okay? We have two things to analyze. One is to uncover the mapping. What's the mapping between I and X? We can either make it very simple and say it's linear or it's log linear. So we make a strong assumption concerning the relationship between y and x. Okay? Or we can go very flexible and make it nonlinear and try to uncover this nonlinear relationship. Okay? If we fix it as linear, it's an easy problem. If we go to nonlinearity, it's a much more difficult problem, but machine learning can help us here. Okay? But that's not the only problem. We have to handle the axis, the covariates. And if the number of covariates is small, if we don't have many covariates, then again, it's a much easier problem. So if we have linearity plus a small number of covariates, traditional statistics, traditional econometrics can solve the problem. So there are not many issues involved. If you have flexible form on the F and a small number of variables, still the solutions can be given by standard nonlinear econometric models. Of course, you can go into fancier machine learning methods, but you're not choosing fancier machine learning methods because traditional models fail. Traditional statistical models can handle nonlinearity with a small number of variables. But the problem kicks in when you start having a large number of variables and flexible forms. How to estimate a model where you don't want to impose linearity and you have a large set of variables. This is the case where machine learning kicks in with a lot of power. Okay? And that's what we want to reach in the end of these 12 weeks that we are going to be together. But we have to start with a simple models first, right? So we are going to start this course with the assumption of linearity, but a large set of regressors. So we are going to start solving the problem of fitting a linear model to a very large set of regressors. Okay? And this is a very powerful tool. And there are many applications, and it's kind of tools that work really well in practice. So we are going to first fully understand this setup. Large number of variables plus linearity. When we are done with that, then we are going to dig into more complicated material, like combining nonlinearity, flexible functional forms, and large data sets. Okay? So that's the idea of the course, okay? That we are going to see in these our next lectures. Okay, so let's start looking into this case where P is larger than T. Okay? So before that, have to bear in mind that the simplest machine learning method that we can imagine is a linear regression. In fact, linear regression is a very nice machine learning method. Okay, and what do we learn with linear regression? Well, we know that for sure we learn the best linear projection of y on covariance x. And for that, an exact solution exists by ordinary least squares, OLS. That under very mild assumptions, we can come up with an estimator of the parameters beta. So beta hat will be x prime x inverse x prime y. Okay? So it's really simple to compute. And why it's the best linear projection? So I invite you to prove these results. So the logic is exactly the same that we use to prove that the condition expectation is the best predictor in the mean squared error sense. So now you do the same kind of proof technique, but using a linear model and not the condition expectation. So the best approximation, the best linear approximation for the condition expectation is given by OLS, okay? And for this estimator of beta. So if we impose stronger assumptions like the condition expectation is linear, okay, then we can OLS give us the estimator for this condition expectation, or if we impose even stronger assumptions, we can even uncover causal effects of changes in x on y. Okay? So linear regression is a great supervised machine learning method. So let's keep this in mind. Okay? Of course, in some cases, linear regression, the traditional solution to linear regression is not a good option. First one, when P is larger than T, when we have more variables than observations. Okay? OLS is just not feasible in this case. Okay? we have, even if we have p less than t, but we have a huge number of observations, matrix inversion is tricky. So that x prime x inverse is a tricky quantity to compute. Okay. In case of nonlinearities, is also a problem for traditional linear regression. Nonlinearities and high dimensions is an even bigger problem, as I already mentioned. Okay, so let me give you an example where linear regression fails. Let's go back to the JFE paper by Moreira and Manella that we discussed earlier. So in their paper, y is the VIX and x is a vector with 468,091 one or two word n-gram frequencies from Wall Street Journal front pages. So what's this axis will be the appearance of an n-gram I in month T divided by the total number of n-grams in month T. But now you ask, what is an n-gram? So an n-gram is a contiguous sequence of n items from a given sample of text or speech. For example, if you take the text to be or not to be, 1 gram, it can be to be or not to be. This is the 1 gram. Now, n grams, the two combinations of two words that are close together. So, to be or not, not to be. These are the n grams. Okay? So, they compute these words for Wall Street Journal. So they have these variables. Imagine how big is this set of variables. See? Almost 500,000 of variables. Impossible to run a regression. They want to use these axes to explain the movements in VIX. A linear regression is just unfeasible. You cannot run OLS. Okay? And they were looking at 5 categories of possible words that were related to war, financial intermediation, government, stock market, and natural disasters. As I mentioned before, we are going to look into this paper in more detail when we study support vector machines. That's the technique that they use. Okay? So basically, this is a quote from George Box that's really important. All models are wrong, but some are useful, right? Linear regression is a useful model, especially when you have a small set of regressors, okay? And the relationship is linear, but it's a good linear approximation. But sometimes we have to go beyond that, and new machine learning models, methods, and algorithms are being proposed every day. So old models are being rediscovered. From now, regression trees, neural networks are being rediscovered. Okay? So which model should we use? Linear or nonlinear? Parametric, non-parametric, semi-parametric? How will we select variables? There are so many ways of selecting variables. There's a high risk of cherry picking. That's data mining in the bad sense of the term. So you are mining the data until you uncover a relationship that you for any reason you like, but that relationship can be completely spurious. So we have to take care about not going into spurious relationship. Okay? So we have to learn what's the goal. It's prediction, it's causality, both. So just to have names to keep in mind, these are names of methods that you're going to learn during this course. Lasso's complete subset regression, factor models. Okay? So it's a vast number of models. So we are kind of lost in the middle of a zoo of models, and we have to figure out which model to use. So one thing that people always ask me, okay, Marcelo, we learned all these models during FIN 580, but how do we choose? Why I should look at model A and not model B? Okay, so I'll try to give you also some guidance on how to pick a model or a combination of models, a group of models, okay? So we are going to do this in this course. So back to the question, how should we choose a model? If we are like in the forecasting school, we can look at out of sample performance. We can look at a combination of models or a combination of the subset of models. But it's an open question. And there is no free lunch. There's no universal best model. One model can work in one situation very well and very poorly in another situation. There's not a single modeling strategy that will work fine in all possible cases. That's just impossible. Just doesn't exist. Okay? So, in summary, that we have big data, we have big models, we have big set of models, so we have a big problem that we try to solve. I hope I'll be able to give you the means to solve this big problem with tools, not only to model data, to model big data, but also how to choose which model is the best one, which collection of models is the best one. So let me now move into give you an overview of a class of models that we are going to study in the first third of the course. Okay? So we are looking at linear models when P is much larger than T. So the number of variables in that linear model is much larger than the number of observations. Okay? So we have a single equation linear model as before, P covariates, U is a zero mean innovation. We are going to assume that P, the number of covariates, is in fact a function of the sample size. Okay? So the number of variables grows as the sample size grows. And here, let me make an observation, make a remark. Of course, in most practical situations, that's not going to happen, right? You have a fixed number of variables. It's not that the number of variables that you observe grows when the sample grows. But why are we assuming this? Because we want to develop statistical techniques that work when the number of variables is large compared to the sample size. Okay? And traditional statistical analysis is based on asymptotics. Usually you try to find what are the properties of your estimators, of your models, when the sample size grows. Okay? If we assume that P is fixed, under these asymptotics, in the limit when T grows, P will be smaller than T. No way P can be larger than T, because P is fixed and T is growing, so there will be a certain point where T will be larger than P. So the traditional asymptotics cannot be good approximations, good finite sample approximations for situations where P is larger than T. So how can we overcome this? We can overcome this by creating a new asymptotics where P grows with the sample size. And more importantly, P grows faster than T. So P diverges before than T diverges. So in this case, if we have an asymptotics for this case, these asymptotics will probably be a good approximation for cases in finite sample where T is not larger than P. Okay, so that's the idea. That's why we have this P as a function of T. And to avoid like complicated notation, we are going to omit this dependence, okay? We are going to assume that beta naught is equal to 0, so data are demeaned, and we are also assuming that all explanatory variables are in the same scale, okay? So how we should estimate the parameters? Remember that P could be much larger than T, OLS does not work. And once we have a new estimator, what are the statistical properties of the estimated model? Can we trust that model? Is this estimated model meaningful or is completely nonsense? Okay. So what are the properties of the estimator? And we are going to work a lot in matrix notation. Okay. So bold Y's and bold X's, we're collecting all the sample in vectors and matrices. Okay. So let me motivate you with an example. We have linear regression model. We're doing OLS. T is less than T. I'm simulating a model, a linear model here, okay, with beta is equal to 2. X is a random variable, normal distribution, 0 mean unit variance. Same for U. We have 500 observations, P equals to 1. Okay? So dots here represent the data. Okay? The red line represents the true regression line with beta equals to 2. Okay? And the green line is the estimator of this regression, the OLS estimator. And you can see this is the sum of squares as a function of beta. So you see if the minimum is here, very close to 2. So you see, you can barely see the differences between the red line and the green line. But here we have many observations. T is much larger than P. So that's where OLS works just fine. Now let's go to the other extreme. Okay? I have one single point, one observation, not 500, one. Same model, okay? We want to fit a line. Well, there is solution, the solution is unique. And why the solution is unique? Because we don't have an intercept here, so we are trying to find the best line, okay, that fits the data and cross the origins of the axis. So that is the green line. Okay? So beta hat, the estimator, is unique, is very close to 0. If you have all the 500 data points, then you see that you're completely off. But why is that? Because you have just a single observation, so this estimator is not reliable. You don't have enough observations. Okay? OLS is really bad, although the solution is unique. Now imagine the case where you have two covariates, no intercept, one observation. So you have more variables than observations. So you want to fit a hyperplane with just one point. So what you have, if you look here, that's the sum of square errors as a function of beta 1, beta 2. In some directions, you have some curvature, but you see that across these lines here, these directions here, you have, it's kind of a piecewise linear function. And you have a kind of a plateau here, where your sum of squares is just constant. And here you have, so in these areas, you have like infinite solutions that gives you the same sum of squares. So when you have P larger than T, you don't have a solution. You have it's underdetermined. So you cannot solve the problem. Okay? You have more unknowns than restrictions, right? You don't have enough observations. Okay? Now that you put here one observation, now I'm going to, in the screen, you're going to see with two observations. So we start to have curvature. Okay? But still, you see that you have a unique solution, but it's completely off. Now let me start adding observation. So you start getting curvature in your function. See, now that looks like a quadratic function. Okay? And if you include more and more, now 10, 500. With 500, you see that you have curvature because you're introducing more observations, okay? And then you can solve the problem. You're going to solve the problem very precisely. Okay? So, with more observations, you're going to estimate the estimator precise and you have unique solutions. When you have less observations than covariates, you have infinite solutions. Okay? So how we're going to solve this problem? Because we cannot say our one solution, the obvious solution, that collect more data. But that's usually not possible. So how we are going to solve the problem? We are going to modify the cost function. And what I'm going to show you in the next lectures is that if we include an additional term here, a penalty term, that's our penalty, okay, we will introduce curvature in the sum of square function, even if we have less observations. In fact, we're going to introduce curvature in our cost function. So we are including an additional term to the sum of squares. So this penalty term here will be a function of the parameters and can be determined by the data, can be data dependent, and also some hyperparameters. But the important that it be indexed by this lambda. This lambda is called the regularization parameter. And the larger the lambda, the stronger will be the penalty. So here are done some possibilities like a square penalty, absolute value penalty, a combination of the absolute value with the square. Okay? So this will give us a solution to the problem. Okay? So this lambda will control the number of parameters in the model. Okay? So if lambda equals to infinite, it diverges, no variables will enter the model because it will be the cost function will be just the penalty. If lambda equals to 0, we are going to have OLS. So there's a trade-off which lambda to choose. And also we are going to learn like data-driven methods to determine lambda. So what's going on here is a trade-off between fit and complexity. Okay? So the larger of the lambda, we are reducing complexity of the model, but we probably decreasing the fit. If we increase complexity, the fit will be better, but at a higher complexity. So we need the trade-off between these two. Okay? So which kind of estimators we are going to learn? The first one, very simple, is the ridge regression, where we are going to include a square penalty here. So the good thing about the ridge, it's going to shrink. It's also called the shrinkage estimator. It's going to shrink the coefficients towards 0. Okay? And how much shrinkage will depend on the lambda. Okay? And the good thing about the ridge is that there is an analytical solution. Okay? Next week, we are going to look deeper into the ridge to learn what exactly this estimator is doing. Okay? But so for now, I just want to give you an overview of the estimator. And here we have the analytical solution. So it's basically very similar to the OLS, but we are kind of introducing a term on the diagonal matrix of X prime X, on the diagonal of the matrix X prime X. Okay? This estimator is very good to prediction, but if we want to do variable selection, what's variable selection? Select the best subset of X. So remember, X is really large. We want to select a subset of X that's most important, or the most important features to explain the behavior of Y. We are going to see that ridge can be a very good tool if we just want to predict Y. But if we want to do variable selection, that's not the best solution. Okay? Ridge also can be seen as a constraint optimization program. That equation here, that minimization problem here, is equivalent to minimize the sum of squared errors subject to a quadratic constraint. So basically what we have here, the surface of this function here, and here we have the quadratic constraints. So the unconstrained minimizer is here, but we want a minimizer that's subject to that function here. Okay? So for different values of lambda, here's the solution path. And what will be the solution will be the intersection of that curve of the sum of squares with the restriction curves. So each level here represents one value of this constant here that is a function of the lambdas. Okay? So this is ridge. So, but now let's imagine that our model is sparse. What's a sparse model? It's basically saying that we have this large set of variables, but only a very small subset of them is really important. The rest is garbage. We can throw them away, but we don't know which ones are important and which ones are not. Okay? So imagine that we split our vector x into components. The component xs, that's the relevant variables, and the component of the irrelevant variables. And we make the same distinction about the coefficient beta. Okay? So what we want to uncover this distinction between beta S and beta SC. We want to figure out which are the relevant variables. Okay? So if we have this assumption, we can move to another estimator that's called the least absolute shrinkage and selection operator, that we make a small change in the penalty. Instead of having a square function here, we have an absolute term. This small change makes a huge difference, because now we can do variable selection. Basically, we can uncover the sparsity structure of the model. Okay? We still shrink the coefficients towards 0. Okay? I'm going to show you that the value of lambda can be recovered with the best, the optimal value of lambda. And you can handle many more variables than observations. Okay? And under some conditions, we recover the sparsity structure. So what Lasso is doing, we have the same analogy, direct analogy to a constraint optimization problem. The Lasso solution is the solution of a restricted sum of squared errors. But now what you see is that the restriction surface is not a ball anymore, it's a diamond. And the solution will be the intersection of the sum of square surface with the diamond. Okay? So comparing with the ridge, you see that here you have a ball and the solution is the intersection here. The solution of the Lasso is the intersection here. And why Lasso can do variable selection and ridge not? Because it will be very, very difficult to the because this is continuous, you have no kinks in the surface. It will be extremely difficult to the intersection of this curve here with the restriction surface is exactly the 0 point. On the other hand, the Lasso restriction is full of kinks. And the larger is the data set, the larger is the number of parameters, the larger is the number of kinks. So there is no negligible probability that the optimal solution is an intersection of a kink with the sum of square surface. So you can estimate coefficients exactly equal to 0. Not close to 0, but exactly equal to 0. Okay? So that's a comparison, another comparison between the ridge and the Lasso. Okay? All right, but the Lasso does not work well if your regressors are highly correlated. If you have regressors very, very correlated, Lasso doesn't work well. What does it mean does not work well? It cannot really select the true set of variables. So there are two alternatives for this. One is called the adaptive Lasso, where basically you make another small change. You include a different weight for each coefficient. Usually these weights are estimated by a pre-estimator, can be the Lasso or the ridge. Okay? And the idea is that you're going to give a different penalty for different coefficients. And as we are going to see during the course, this small change can make kind of decorrelate the variables. And you can, in a much easier way, distinguish between relevant and irrelevant variables. Okay? So that's exactly what I said. Another solution is what's called the elastic net, that you combine the ridge penalty with the Lasso penalty. And there is an alpha term that weights between the two penalties. Okay? Again, the motivation is correlated regressors. Okay? So this part here will generate a sparse model. And the quadratic term will do what we call the grouping effect. Would like try to select variables that look similar. Okay? And also we have the adaptive version of the elastic net. Okay? So comparing the three restrictions surfaces, the dashed blue lines is the Lasso, the dashed circle is the ridge. So what elastic net does, it introduces curvature here but still keep the kinks. So elastic net has the kinks, so it continues to do variable selection, so it induces a sparse solution, but it introduces less penalty here in this region. So it's a kind of trade-off between lasso and ridge. Okay? So how these things introduce curvature when P less than T? So remember the surfaces when P less than T and no penalty, right? Now ridge penalty. You move from this surface to that one. A lot of curvature, right? So you solve the problem. You introduce curvature in an almost flat function. That's the lasso penalty. Many kinks, see? And that's because of the restriction. That's the elastic net penalty. You have a curved region, but with kinks. But so you see here the magic going on. You introduce these penalties and you introduce curvature, so that makes possible to estimate the parameters, right? So next lecture, we are going to learn what, in fact, these methods are doing. Okay, you estimate a parameter, but can we trust these estimates?